You know functions, you might even know derivatives. But let me ask you something nobody asked you in calculus class. What's between them? A function sits at one spot, its derivative sits one step over. I want to know what lives in the gap. Can I take a half derivative? And for this, we need half to really earn its name, like a square root. Root 9 is the thing you multiply by itself to get 9. So a half derivative is the thing you apply twice to get one whole derivative. Now that might sound like some nonsense, but it's not, and the question is over 300 years old. In around 1695, right after Leibniz invented his notation, he got a letter from L'Hopital. Yep, the same one, the rule guy, asking the obvious troublemaker question. What if n isn't a whole number, something like 1/2? Apparently, Leibniz wrote back, and this is basically the real quote, an apparent paradox from which one day useful consequences will be drawn. And he was right, it just took a while. So how might we go about building something like this? Take, for example, x squared. By the power rule, its derivative is 2x. Multiply by the power, subtract 1 from the power. So maybe its half derivative should be something like 1.5x to the 1.5? Well, the issue here is if you apply that same rule again, you get something weirder when we should get 2x. And this gives us our first real insight to how these half derivatives should work. Differentiating doesn't just lower powers by 1, it throws off the coefficients in a very particular way. X to the 4th goes to 4x cubed. X to the 7th goes to 7x to the 6th. So whatever a half derivative is, it has to know exactly how much coefficient to release on each half step. So where do these coefficients really come from? If you take n derivatives of x to the k, you might notice a pattern and get this formula. You can check it against our examples, and it works. And so now our plan is pretty obvious. Plug in n equals 1/2, and immediately we get an issue because traditionally k factorial only makes sense for whole numbers. And our formula would need fractional factorials. And so if you're a longtime viewer of this channel, you know where we're going. It's the gamma function. The famous gamma function fills in the factorials in between the whole numbers, and still acts like factorials at those whole numbers, keeping everything working how it should. So let's just rewrite our formula with gamma function notation. And now we should be able to plug in pretty much whatever we want. How about 1/2? We'll just take a simple example. Take our function to be x. What's the half derivative of x? Well, according to this formula, that's gamma of 2 over gamma of 3/2, x to the 1/2. Now, you do need to know something about the gamma function with these half factorials. That's another video, but gamma of 3/2 is root pi over 2. And so the half derivative of x is 2 by root pi root x. Now, that's pretty strange. I don't see any circles lying around, but for our rule to hold, we should be able to take this derivative again and get to the true derivative of x, which is 1. So, throw it into our formula again, take the half derivative. There's another gamma of 3/2. That cancels with our earlier gamma of 3/2. Gamma of 1 is just 1, x to the 0 is 1, and the whole thing collapses to 1. 2 half derivatives gave us 1 full derivative, at least in this case. How about with our earlier example of x squared? Take the half derivative of x squared, deal with some gamma function things, do it again, and hey, there we go, we get the expected result 2x. Now, I know what you're saying, that's all well and good for power functions, but what about other types of functions? What about exponentials or trigonometric functions? Well, every time we differentiate e to the ax, you basically just multiply by a factor of a. So the natural choice here would be that we multiply by a root a instead of a. Do it twice, you get the first derivative. How about something like sine x? The derivative of sine x is cosine x, which, if you think about it, is basically just a shift, a translation of the sine function. So a half derivative should just be half of that translation. Translate it by pi over 4 rather than pi over 2. Do it twice, you get this relationship, which is cosine. So where are we at with everything? If we treat the function itself like order 0, the derivative is order 1, positive 1. Going the other way, integration would be like negative 1. And they're sort of not really three separate ideas, they're 3 points on one continuous line. And now, with these fractional ideas, we can sort of stand anywhere along this line. But there's another interesting aspect of this. The first derivative of a function has a picture, its slope. So does its second one, how the graph curves or bends. What would the half derivative look like or represent? Well, here's the frustrating part, there's not really a clean answer. After these 300 years, there's not really an agreed geometric meaning for a fractional derivative. People have definitely proposed one, but none of them stuck with me in the way that slope did. There is another kind of tangle to this. Our half derivative is supposed to handle any function, not just powers and exponentials, and when you tie it together with one definition, it comes from rewriting repeated integration, and surprise, that formula also hides a factorial you can swap for the gamma. This is sometimes called the Riemann-Liouville derivative. And it does something that should probably bother you. Take the half derivative of a constant. Just take the derivative of 1. Now, the regular derivative of 1 is 0. But the half derivative of 1 is 1 over root pi x, not 0. A flat function has a half derivative that isn't flat at all. The reason is that a fractional derivative isn't local. The normal derivative only looks at one instant, the slope right where you're standing. A half derivative looks at the function's entire history. It's an integral over everything that came before. It sort of has memory. Which is probably why no simple picture ever really stuck. A slope is something you can see at a point. A half derivative isn't at a point at all. It's smeared across everything the function has ever done. And this is probably why mathematicians keep more than one definition around here. The version that sends a constant to 0 is a different one. And which one you use depends on which situation you're modeling. And people do model with these. That memory effect is right for materials that are part solid, part fluid, gels, polymers, living tissue. It shows up in diffusion that runs faster or slower than it should, and in control systems that need finer tuning than the standard ones allow. So Leibniz's paradox did pay off, and it took about 3 centuries. And speaking of questions that pay off, I want to tell you about today's sponsor, Brilliant. I teach math for a living, and what worries me most right now is AI just handing students the answer. It gets the work done, and the thinking never happens. This is where Brilliant's new tutor Koji comes in, and it works the opposite way. Check out how it works with this problem. I don't know where to start.
Let's try a test point. Where should -1, -2 move to?
Is it this one?
That's right.
Yep.
So -1, -2 goes to -2, 1. See a pattern?
This one and this one.
You got all of them right. Perfect lesson.
The whole process is like that. Whether you're in a lecture hall or you have a kid grinding through math homework, this is what I wish every student had at home. Endless patience and no tutoring bill. Click the link below or scan the QR code to get started with Brilliance Tutor for free. You can upgrade to Premium to unlock all courses, and right now, Bri the Math Guy viewers can save 20% off an annual subscription at brilliant.org/Bri the Math Guy. We've filled in the gap between a function and its derivative. It's like there's this smooth dial of half steps and even quarter steps. Really, almost anything you like. You can take a derivative of order 1/2 and square it right back into the real thing. What that thing looks like is still sort of up for grabs. If you like these mind-bending calculus situations, I think you're really also going to enjoy this video on the screen. Click it right now to watch. I'll see you in that one.
This single equation helped unlock the modern world. It gave us computer chips, electron microscopes, atomic clocks, GPS, high-speed internet. The list goes on. But where did this equation come from? Well, according to Richard Feynman, it comes from
nowhere. Out of man's imagination struggles with the details of experiment and all kinds of mysteries.
That man was Erwin Schrödinger. He derived it in 1925 while vacationing in the Swiss Alps with his mistress. So I have two questions. First, how can we intuitively build this equation ourselves from scratch? But secondly, why is an equation with such real impact built using an imaginary number? What's I doing there? If you're ready, let's find out. It all starts in 1853 when the physicist Anders Ångström finds that hot hydrogen gas gives out very specific colors of light. We soon figured out it's not just hydrogen. Every hot element gives out its own signature spectrum. And suddenly, this became a powerful tool to discover brand new elements just by looking at their light. This is how we discovered helium for the very first time in the sun. So in his honor, the unit for measuring these wavelengths was named the Ångström. But nobody knew why these elements gave out those specific colors of light. The first clue actually came a few decades later from a Swiss math teacher named John Balmer. Balmer was obsessed with numbers and patterns, and he finds a surprisingly simple formula for the hydrogen spectrum just by trial and error. And the formula predicts there should be more lines, and we actually confirm it. But nobody had any clue what this formula meant. Why did it work? To answer this, we needed a good theory.